Yeah, in the yesterday's class, we started magnetostatics. In that class, we discussed about the basics of magnetostatics. That is, force acting on the charged particle placed in the magnetic field. Okay, by using that force equation, we defined the magnetic field or magnetic induction, and we finally talked about the magnetic flux. Okay. In the today's class, we will be discussing about Biot-Savart law and its applications. Okay. The outline of today's class is okay. This is the outline of today's class. Yeah. In this class, we will discuss about the superposition principle at first. After that, we will be discussing about Biot-Savart law, and next we will be uh, studying about one application of Biot-Savart law to find the magnetic field of a infinite straight conductor. Okay, right. Yeah. First of all, let us study about this superposition principle. Yeah, we have already studied the superposition principle in electrostatics as well. Okay, there we applied this superposition principle for the electric fields created by different charges placed at one location, placed at one uh, area. Okay. Similarly, we also studied the superposition principle applicable for the potentials as well. Okay. If there are more than one charge at a place, then to know the total potential at some point, we apply the superposition principle for potential as well. Okay. In case of electric field, you have superposition principle as yeah. In case of electric field, you have E is equal to say some E1, E2 plus dash dash dash. Okay, these are all the vectors. Okay. Next, the same superposition principle also applicable for the scalar, that is potential. Phi total potential is equal to potential due to uh, all the charges, sum of the potentials due to all the charges, phi 1, phi 2 plus dash dash dash. Okay. Here, this sum is a scalar sum. Here, this sum is a vector sum. Okay. Next, here, uh, coming to the magnetostatics, these magnetic fields are also created by the charge in motion or current. Yeah, this was discovered by the Oersted. So in this case also, experiments showed that the superposition principle is equally valid. Okay. That means you consider so many charges in motion at one place, then the total magnetic field induced by all these charges B is equal to, say that is B is equal to B1 plus B2 plus dash dash dash. B1 plus B2 plus dash dash dash. Okay, B is equal to B1 plus B2 plus dash dash dash. Okay, right. So superposition principle is also applicable to, okay, applicable to magnetic induction vector as well. Okay, magnetic induction vector as well. Okay, if you are having the scalar, that means magnitude of this B, then you simply have to add the individual magnitudes. Individual magnitudes. Right. This is a this is experimentally verified formula. Okay. So superposition principle also applicable to the magnetic induction vector. Okay. Yeah. Why we are studying the superposition principle here? Why? Because whenever we go for the Biot-Savart law, there Biot-Savart law gives you infinitesimal field, say dB, to get the total induced magnetic field. What you have to do, you have to add all those dBs, okay? That is in the form of integral. Right. That's why here we are studying the superposition principle before going to the Biot-Savart law. Okay. All right. Here, why here, since from the last class we are studying that the fields are due to the currents or the charges in motion. You have to consider one important thing you have to keep in mind. Charges in motion will create the magnetic field. Charge in motion means currents. Charges in motion means currents. That means what are the sources of magnetic field? A charge in a motion or a current. Okay. Charge in a motion or a current. Okay. So how can you know that? You can know this from the formula which we discussed yesterday. F is equal to QB cross B. Okay. Yeah. In the previous class we considered this magnetostatic force formula to define B. Okay. That's why we did not discuss today thoroughly about this formula. Actually, it's a part of the Lorentz force. Lorentz force. You will find this expression as a part of the Lorentz force. Okay. Here, this formula is very important formula which gives the magnetic force as a product of two vectors, velocity and magnetic induction. Velocity and magnetic induction. Okay. Here we assumed some special cases in the previous class. Okay. In the today's class, let us take some other assumptions. Say whenever you make this Q 0, what happens then? If you place a neutral particle in the magnetic field, then what happens? Okay, Fm is equal to, or just you take the magnitude formula here, QVB sine theta. Okay, QVB sine theta. If you are making Q is equal to 0 for any theta, whatever may be the direction of motion of the charged particles, if it is having no charge, then what happens? This is 0, so everything will be 0 for any orientation. So on a neutral particle, if you place a neutral particle in the external magnetic field of induction B, then you have no magnetic force. Why? Because magnetic field interacts with magnetic field only. Okay. Fm is equal to 0 while there is no charge on the particle. Next, second thing is when B is equal to 0, this is very important case. When B is equal to 0, Q is not 0 here. Okay. Then what happens to the above formula? Fn is equal to. Okay, I will write here. Yeah, second case, when B is equal to 0, that means your particle is still a charged particle, but it is not moving. It is a stationary charge placed in the magnetic field. Particle is there, that too charged particle, but it is stationary. It is simply placed at a place in the external magnetic field. Then what happens to the magnetic force? Fm is equal to Q. Now the second term is 0. Second quantity B sin theta, whatever may be the value of theta, arbitrary theta. Now also you have magnetic force 0. Okay, when V is equal to 0, Fm is equal to 0. When V is equal to 0, Fm is equal to 0. What is the meaning of this? That means you are having both the charged particle and magnetic field at the same place, but there is no effect of magnetic field on these charged particles. When the magnetic field affects the charged particle placed inside of that, if and only if that particle is having a non-zero velocity. Unless and otherwise the particle is moving, magnetic field does not exert the magnetic force on the particle. This is a very important conclusion. Okay, why magnetic field is not exerting the magnetic force? Magnetic field only interact with the magnetic field. So when the particle is stationary, it will not create any magnetic field. It will not create any magnetic field. That's why external magnetic field does not exert any force on the stationary particle placed in the external magnetic field. That's why what is the source of a magnetic field? Not the stationary charge, a charge in motion, or this is nothing but current. Okay, that's what again I am discussing about this formula. So what is the origin of magnetic induction here? A charge in motion, not the stationary charge. A charge in motion. A charge in motion means that is nothing but the current. We call that as the current is flowing. Okay, this is a very important thing you have to remember. A stationary charge cannot, irrespective of the external field, it cannot it cannot induce the magnetic field. Okay, magnetic field. If this charge or the charges are moving steadily along one conductor, then they will create a magnetostatic field. Magnetostatic field. This you have to remember. It is very important thing. Now let us go for our main topic, that is Biot-Savart law. Yeah, most of you already know the Biot-Savart law. Okay, it was experimentally discovered that field induced by a current carrying conductor is proportional to certain things. Okay, depends on certain things. What factors influence the field created by a current carrying conductor? This was discovered experimentally so many years ago. Okay, if you sum up all those things in a concrete form, then we call that expression as a Biot-Savart law. Biot-Savart law. Okay. Here you can see on this slide the factors influencing the induced magnetic field. See what factors are influencing the induced magnetic field. Okay, I see. Suppose that you are making a very long conductor that may be in any shape, that may be arbitrary conductor, that need not to be a straight conductor. Okay, Biot-Savart law applies for an arbitrary conductor, whatever may be the shape, curved shape. It is something like curve. Okay, its length may be say d, its length, total length may be L, but what we are considering is only an infinitesimal element of that wire. That means dl. Okay, what we are observing is how much magnetic field induced by that infinitesimal length of the current carrying conductor. Okay, we are taking only infinitesimal element dl of the conductor. Corresponding magnetic field corresponds to dB induced magnetic field. It corresponds to dl corresponds to dB induced magnetic field. Now we are going to study what factors influence the dB. What factors influence the infinitesimal element of the magnetic induction? Okay? Yeah. People discovered that experimentally dB depends upon so many factors. dB, you see on the slide, is proportional to I. See, the same current flows through all along the length of the conductor. So, whatever the infinitesimal element we take, you may take that infinitesimal element in any part of the conductor, then you have only the same current, it is I. Okay? So, the current itself influences the induced magnetic field. Actually, this is what the source of a magnetic field. So, it is very obvious to imagine that dB is proportional to IA, current flowing through the infinitesimal element. Okay, you see, I will draw here the conductor. So, say some I current is flowing through this. Okay, you are taking some part of the conductor. Say this is a DL. Okay, this is what the direction of DL. What is this? DL. Here to here, this is DL. You want to find here, you want to know the magnetic field. Yeah, this is at the distance R from the DL. How much angle it is making with DL? Say theta. Okay. See, what is the angle between infinitesimal element, direction of infinitesimal element, and R? Theta. Okay. Now, the magnetic field induced by this small element dl at a point P is dB. Okay, here you have dB magnetic field. That magnetic field is proportional to I. Okay. Furthermore, what the people discovered is this dB also depends on length of the infinitesimal element. If you are increasing the length of the infinitesimal element, here also dB is proportional to I, means as you increase the current flowing through the same conductor, then you have more magnetic field at the same point located at the same distance from the infinitesimal element. You are just changing the current, that simply changes the magnetic field over here. But that means dB is proportional to it. If you increase the magnitude of the current flowing through the conductor, then obviously you have more induced magnetic field at the point under consideration. Okay, next, this dB induced magnetic field, infinitesimal induced magnetic field, also influenced by the length of the infinitesimal element. If you increase the length of the infinitesimal element, if you increase its length, Then what happens? Here, the induced magnetic field also increases. Induced magnetic field also increases. Okay, right. Why? Because the length of the conductor is increased. Okay, that's why the magnitude of dB is also increased. Magnitude of dB is also increased. Next, this dB is also influenced by theta or sine theta. People discovered that this dB is proportional to sine theta. That means the way where you are choosing that point from DL, what is the orientation of that point with this infinitesimal element? That also influences the induced magnetic field. Okay, as you increase theta, what happens? Tan theta value increases, so dB value also increases. This was also found experimentally so many years ago. Okay, right. Next, what other factors found to influence the dB? Finally, people found that dB is also influenced by the length of this R. That means where the point is located from the conductor. So if your point is far away from the conductor, it is most obvious that their induced field may be very small. Why? Because you are moving away from the source current or the conductor. That too, it varies as R square. It varies as R square. dB, it was found experimentally that dB is inversely proportional to R square. So, these are all the factors 1, 2, 3, 4. These 4 factors found to influence the magnetic field, induced magnetic field of a current carrying conductor. So if you sum up all these three things into a single formula, then you have if you sum up all these things, you have your dB, your dB is proportional to I dl sine theta by r square. So a single statement of all these 4 statements is dB is proportional to ideal sine theta by r square. If you remove this proportionality sign, you have to introduce proportional constant. So here this is magnetism, that's why you have mu naught by 4 pi I dl sine theta by r. So your dB is now mu naught by 4 pi I dl sine theta by r square. Ideal sine theta by r square. Okay, this is nothing but the Biot-Savart law. Biot-Savart law. You can see here this. Okay, this is nothing but Biot-Savart law. dB is equal to mu naught by 4 pi I dl sine theta by r square. This is called as Biot-Savart law of magnetostatics. Okay, you can see this on the slide also. Okay, but this is a scalar form. This is the scalar form of Biot-Savart law. Okay, what is the vector form of a Biot-Savart law? The vector form of Biot-Savart law is the vector form of Biot-Savart law is, okay, how to convert it into the vector form? You can see that on the slide. Okay, how to convert this into the vector form? dB, vector dB is equal to, okay, vector dB is equal to, here this is mu naught by 4 pi, okay, mu naught by 4 pi. Here, yeah, you write ideal, okay, cross ideal cross R by R cube. Now you expand this, you will get the same formula. Right. So you can write without any difficulty this formula as this formula. But this is a vector form of Biot-Savart law. This is a scalar form of Biot-Savart law. Here we are considering this vector equation in your graduation. Okay, previously you know this is scalar formula, but here we are also taking the vector formula of the vector form of the Biot-Savart law. You can see the same thing on the slide as well. Okay. Now, if you want to find the total magnetic field due to the entire conductor, then we are having so many dBs. Okay, what you have to do here? What you have to do here? Okay, in order to get B, what you have to do? Now you have to take integral of dB. Integral of dB. Yeah, you can also write this for scalar form. Okay, B is equal to dB. Integral dB. Integral dB. So here you have B is equal to, what is dB? Mu naught by 4 pi, I am taking scalar form. Mu naught by, okay, 4 pi ideal sin theta by r square, na? Okay, integral I dl sin theta by r square. Okay, this formula will give you the magnitude of total magnetic field induced by the total conductor. Okay, induced by the entire conductor. So here this is nothing but adding all dBs. Okay, this is nothing but, here we are using superposition principle. This means this is dB1, okay, dB2, dash dash dash, all infinitesimal elements. We are adding the induced magnetic field due to all infinitesimal elements. Okay, dB1, dB2, okay. Right, for each and every infinitesimal length is inducing this much magnetic field. Okay, if you are taking first infinitesimal element of length, it is creating dB1. Next, if you are taking second infinitesimal length, then it is creating dB2. Now, what will be the total magnetic field at the point P? That is given by dB1 plus dB2. This is according to the superposition principle. Okay. Yeah, this is about the Biot-Savart law. Biot-Savart law. Okay. Yeah, now let us go for the applications of this Biot-Savart law. Yeah, Before that, as I already told to you, this V is a vector. Now the question is, now you see this slide. Yeah, now you can see this slide. Oh, yeah. As I told to you, this dB or V is a vector. Okay, then you get the doubt that what will be the direction of the induced magnetic field? What will be the direction of induced magnetic field? Okay, yeah, this is say this is your conductor. You are taking your DL somewhere here. Suppose that you have the very option that considering the point here, or you may take the point here. You have the very option that taking the point on this side or that side. Okay. You have the option for that. Yeah, you see here. You may choose your point here or here, somewhere else, wherever you need. Suppose that you want to find the induced magnetic field on the right side or left side, whatever it may be. Your point may be anywhere. Here, you see this slide. You have magnetic field over all the sides. See here. Yeah. In one diagram on the slide, you have your point on the right. And another diagrams are from the right. Second diagram, you have your point on the other side. Okay, left side. Okay. See here, in both cases, you have the directions of P. Okay, directions of that point. Okay. Here, the direction of magnetic field at that point. Okay, sometimes that is shown in the slide. What will be the direction of magnetic field if you are choosing a point at this P? Okay. What will be the direction of magnetic field if your point is P prime? If your point is P prime, how to find the direction? According to Biot-Savart law, this induced magnetic field is dB is equal to, yeah, I'm writing here, dB is equal to mu naught by 4 pi IDL cross R by RQ. IDL cross R by RQ. This is a vector, this is a vector. So this vector, dB vector, is the cross product of two vectors. Okay, DL or IDL into R, cross R. Yeah. It is a cross product of DL and R. So by using the right hand rule, you can find the direction of induced magnetic field. Okay, this we studied in the case of this right hand thumb rule. We studied in the case of Oersted's discovery. Okay, if you are having the straight conductor, then you know how to find the direction of the magnetic field. Okay. Here also, if you take any one part, a part of the conductor that can be treated as a linear, there you have to hold that conductor with your right hand so that the thumb is along the DL. Then the direction of your fingers will be the direction of the magnetic field, induced magnetic field. Okay. See, in one diagram, when the point is on one side, on the right side, the direction of B is different. If your point is on the left side, then it will be different. Direction of B will be maybe different. See, in one diagram, you have the direction like this. Okay, this is the direction of current. This is the direction of current. Okay. In the second diagram, you have the direction of B like this dot. Okay. I already told you that there are two ways possible, two directions possible, and we denote those two directions like this and like this. Okay. This is a way of showing the direction of magnetic field. What is the meaning of this and this? Whether this way of writing the direction is correct or not. In this case, we have to check with the right hand thumb rule. Okay, if you hold the wire like this, see, this is the direction of your current. Your fingers, suppose that I am taking that conductor into my grip by pressing my fingers into the board and bringing them back out like this. Then here on the other side, okay, the left side of conductor, my fingers are coming out. That's why this is the dot. Direction of magnetic field is upwards from the board. See, as I hold the wire like this, on this side, my fingers are again entering into the board. That's why here there is a cross mark. That means your magnetic field is inside of this board. Okay, here your magnetic field outside of this board. Okay, this you have to know. On either side, you cannot have the same direction of the magnetic field. The direction of magnetic field interchanges as you go from one side of the conductor to the other side of the conductor. Okay, this is the way to find the direction of induced magnetic field. Induced magnetic field. Okay, right. Here, this is your DL. This is your DL. Okay, this is your R. This is your R. Okay, you see, just you place your fingers on the board plane. See, on the board you are having both RDL vectors. Put your fingers on the board like this and okay, and try to bring the DL vector onto R vector. Then your finger is inside of the board. So the direction of magnetic field is inside. In this way also you can find the direction of induced magnetic field. Otherwise, if you go for the other case, left side, you put your fingers on the board like this, then bring your DL to R, then what will be the direction of your thumb? Outside. So you are having dot here. In this way also, you can find the direction of induced magnetic field. Why? Because B is a vector, you must be in a position to tell what is the direction of that vector. Magnetic induction vector. So in these two ways you can find the direction of induced magnetic field. Direction of induced magnetic field. Okay. Yeah, people will also find the direction by placing the first three fingers perpendicular to each other. Okay, and aligning one vector, okay, in RDLs and along one finger, okay, and another vector in another finger. Then your thumb will be giving you the direction of the induced magnetic field. Okay, I like this. Then your thumb direction will be the direction of induced magnetic field. Okay, this is also another way of finding the direction of B. One thing you have to note here, B is expressed as a cross product, okay, of two vectors. That will help you to determine the direction of the magnetic induction vector. Okay, see, just discussing about the magnitude is not enough here. Why? Because B is a vector, so you must have to discuss the way of finding the direction of the induced magnetic field given by the Biot-Savart law. Okay, just you cannot leave it like that. Here you have to discuss about the direction of the induced magnetic field as a part of Biot-Savart law. Why? Because we are expressing the Biot-Savart law in the vector form. That will greatly helps you to find the direction of induced magnetic field. Okay, right.
Okay, thank you.